So whenever it comes to any of these 2D relative velocity or motion problems, the first thing that I do is I always draw the situation or whatever's happening in the problem. Now with this, because they give us a coordinate that is two-dimensional, right? The 7 degrees south of east, that means that it's in quadrant 4 here. So my vector arrow of 450 kilometers per hour would be in between south and east. And then when it says the wind blows from the west, this actually means east because it goes from the west towards the east. It doesn't say it blows west. The other thing to keep in mind here is that the ground is going to be sort of horizontal, right? And that every vector arrow that we're drawing represents a magnitude that would be seen from the observer. Now that 450 kilometers per hour is relative to the wind that is already going 80 kilometers per hour. So that means that an observer from the ground is likely going to see that plane going a lot faster than 45 kilometers per hour because it's not moving at all. Now that 70 degrees would be between the direction of the wind. And again, this is not what the observer sees, right? That 450 kilometers. Okay, that is what, if you were already traveling 80 kilometers per hour, that's how fast the 450 kilometers per hour, that's how fast it would seem to go to you. What that means is that we have to break down this vector arrow of x and y relative to the wind. And so you're going to need an x total relative to the wind and a y total relative to the wind. Keeping in mind that the 80 kilometers per hour is actually relative to the ground. And we should also keep note that the 80 kilometers per hour wind is reference to the ground, or how an observer would see, or how fast the wind would be blowing according to an observer. So when I take that vector that's given, which is relative to the wind, I'm going to get the x direction relative to the wind and the y direction relative to the wind. And using a little bit of trigonometry, we're going to mark the y direction as negative because it's pointing south. And now we're going to add up all the x vectors and y vectors together to get our x and y totals relative to the air, of course. Now using the relative velocity formula, we're going to calculate the relative velocity in the x direction, but relative to the ground this time, and the relative velocity in the y direction relative to the ground, of course. Now, since the ground isn't moving, right, that observer velocity is going to be 0. So then it would be the same as the total velocity relative to the wind. And then same thing in our y direction, since it's not moving in the x or y direction, then it is also going to be subtracted by 0. And then finally, the resultant velocity that the observer on the ground would see, and this represents the magnitude of that velocity, that would be the x total relative to the ground connected to the y total relative to the ground, and using our Pythagorean theorem, we get a value of about 483 kilometers per hour. And this makes sense because if the original velocity was relative to an air speed that is already going 80 kilometers per hour, it makes sense that an observer that is stationary would see this plane going faster.